I will introduce the second set of hydrocarbon critical constants and specific gravity data. Additional rows for liquid-specific gravity follow, based on 60 degrees Fahrenheit, ranging from 0.5220 to 0.6861, and values with Note 7 were measured under the 60 degrees Fahrenheit saturation pressure condition. Gas-specific gravity is a relative value with air as 1, showing repeating values like 0.9686. 1.4529, 1.9372, and 2.5125. If the gas-specific gravity is greater than 1, it means the gas is heavier than air, which serves as the basis for determining whether a leak will settle on the floor or rise. Values in parentheses, such as 558.4, are estimated critical pressures. This set corresponds to the continued data of the hydrocarbon physical properties table.
I will introduce the boiling point column. This header is for the boiling point column, with a reference pressure of 14.696 IA and the unit in Fahrenheit. Since 14.696 IA corresponds to standard atmosphere pressure, or 1 atmosphere, the boiling point here refers to the temperature at which a liquid boils at atmosphere pressure. The boiling point is the reference column for determining the volatility ranking of each hydrocarbon. When viewed together with the freezing point, vapor pressure, and critical constants, the phase behavior of a compound can be comprehensively compared.
I will introduce the boiling point column within the hydrocarbon physical properties table of the engineering data chapter. The header of this column specifies the reference pressure as 14.696 IA, which is standard atmospheric pressure, and lists the boiling point under that condition in Fahrenheit. Each hydrocarbon listed in the table, such as methane, ethane, and propane, has a boiling point value measured at this same 14.696 IA reference, so the table is structured to allow a direct comparison of the boiling points of different substances under the same pressure condition.
This chunk summarizes the molecular weights and gas-specific gravity standards for aromatic hydrocarbons. Gas-specific gravity is expressed based on air equals 1 at 60 degrees Fahrenheit. Benzene has the chemical formula C6H6 with a molecular weight of 78.114. Toluene is C7H8 at 92.141, and ethylbenzene is C8H10 at 106.168. Interestingly, ortho, meta, and paraxylene all share the same formula, C8H10, and the same molecular weight of 106.168. Additionally, acetylene is 26.038, styrene is 104.152, and isopropylbenzene is 120.195. The footnotes below the table distinguish the sources of the values. Number 1 indicates calculated values. Number 2 in parentheses indicates estimated values. Number 5 refers to saturation pressure at the triple point, and number 6 refers to the sublimation point.
Continuing in the same chunk, there is a table for the specific heat ratio of gases. The specific heat ratio, K, is the ratio of specific heat at constant pressure to specific heat at constant volume, and it is a key factor in valve sizing calculations for compressible fluids. Acetylene is 1.38, air is 1.40, argon is 1.67, and butane is 1.17. Also, carbon monoxide is 1.40, carbon dioxide is 1.29, and ethane is 1.25. Helium is 1.66, hydrogen is 1.40, and methane is 1.26. Here, monatomic gases like argon and helium have the highest specific heat ratios, ranging from 1.66 to 1.67, while hydrocarbons with more atoms, such as butane, tend to have lower values around 1.17.
This short chunk contains precautions when using property tables. Since the values in the hydrocarbon property table seen previously are general reference figures, it advises using dedicated property tables if higher accuracy is required. In other words, while these tables are acceptable for preliminary reviews, it is preferable to verify detailed property data specific to the substance for precise design or valve sizing calculations.
This chunk corresponds to the boiling point column header in the table summarizing critical constants and freezing points. Similar to the previous boiling point column, the reference pressure is set to 14.696 IA, which is standard atmospheric pressure, and the boiling point under that condition is expressed in degrees Fahrenheit. In this table area, the boiling point is placed alongside critical temperature, critical pressure, and freezing point data, allowing for a side-by-side comparison of the phase behavior of each fluid.
This chunk refers to the header of the freezing point column and the subsequent vapor data column. The freezing point is also expressed in degrees Fahrenheit, with the reference pressure set to 14.696 SIA, or standard atmospheric pressure. In the table, vapor-related data follows this freezing point column, providing comprehensive phase change temperature information for each fluid, along with the boiling point and critical constants seen earlier.
This chunk is the header for the vapor pressure column. Vapor pressure uses 100 degrees Fahrenheit as the reference measurement temperature, and the unit is expressed in SIA, which is absolute pressure. In the table, this vapor pressure data is placed after the freezing point and critical constant columns. By comparing the vapor pressures of each fluid under the same condition of 100 degrees Fahrenheit, it can be used to estimate volatility and behavior related to cavitation and flashing.
Now, I would like to introduce the physical property tables for various fluids used in control valve sizing. This table presents the vapor pressure of each fluid at 100 degrees Fahrenheit in SIA, while also summarizing critical pressure, critical temperature, and liquid-specific gravity. Critical pressure is expressed in SIA, and critical temperature is in degrees Fahrenheit. Liquid-specific gravity is shown as a ratio of 60 degrees Fahrenheit per 60 degrees Fahrenheit, meaning the liquid at 60 degrees Fahrenheit is compared to water at the same temperature. The critical temperature entries include negative values, with some as low as minus 140.8 degrees Fahrenheit. These vapor pressures and critical pressures are important because they serve as key input values when evaluating cavitation or flashing phenomena in valves.
Next, let's look at the key figures in the table. Critical pressures range from approximately 465.4 SIA to 706 SIA, with values such as 552.2, 605.55, 651.4, 675, and 676.4 SIA visible. Vapor pressure at 100 degrees Fahrenheit ranges from about 0.188 to 3.224 SIA, with more volatile fluids having higher values. Liquid-specific gravity, based on 60 degrees Fahrenheit per 60 degrees Fahrenheit, is between approximately 0.615 and 0.911, with most clustered between 0.86 and 0.91. Critical temperatures include both negative and positive values, from minus 140.8 degrees Fahrenheit to 55.86 degrees Fahrenheit. Additionally, some rows provide auxiliary coefficients such as 1.32, 1.40, 1.21, and 1.15, which represent additional properties like the specific heat ratio. The footnotes in parentheses specify measurement conditions, such as number 2 being an estimated value of 0.24, number 5 being a reference value of minus 114, and number 9 providing a clue for the 0.615 specific gravity, so please check them when using the table.
I would like to introduce the concluding part of the previous hydrocarbon physical constants table. In this chunk, a specific heat ratio K value of 1.33 is presented at the end. The specific heat ratio K is the ratio of specific heat at constant pressure to specific heat at constant volume, and it is a key variable for correcting compressibility effects when calculating gas flow rates. The preceding table summarized gases such as natural gas, nitrogen, oxygen, propane, propylene, and steam based on a specific gravity of 0.6, with the steam entry having a separate condition in footnote 1. From this point, we move to the physical constants of various fluids table. This table is characterized by covering a wide range of fluids, including acids, salts, and aqueous solutions, not just hydrocarbons.
I would like to introduce the boiling point header within the column structure of the physical constants table for various fluids. The first data column of this table is the boiling point. The reference pressure is 14.696 SIA, which corresponds to standard atmospheric pressure. Temperatures are expressed in degrees Fahrenheit. Each row is categorized by the fluid name. Since the boiling point is the temperature at which a fluid changes phase from liquid to gas, it serves as basic data for determining whether cavitation or flashing will occur in a valve.
I will now provide a detailed introduction to the first data block of the physical constants table. The table consists of the fluid name, chemical formula, molecular weight, boiling point, freezing point, liquid-specific gravity, and gas-specific gravity, in that order. First, acetic acid has the chemical formula HC2H3O2, a molecular weight of 60.05, and a liquid-specific gravity of 1.05. Acetone is C3H6O, with a molecular weight of 58.08, liquid-specific gravity of 0.79, and gas-specific gravity of 2.01. Air is denoted as N2O2, with a molecular weight of 28.97, a boiling point of minus 317 degrees Fahrenheit, a freezing point of minus 221 degrees Fahrenheit, liquid-specific gravity of 0.86, and gas-specific gravity of 1.0. Ethyl alcohol is C2H6O, with a molecular weight of 46.07, a vapor pressure of 2.3, and a specific gravity of 0.794. Methyl alcohol is CH4O, with a molecular weight of 32.04, vapor pressure of 4.63, and specific gravity of 0.796. Ammonia is NH3, with a molecular weight of 17.03, a boiling point of minus 28 degrees Fahrenheit, liquid-specific gravity of 0.62, and gas-specific gravity of 0.59. Next, items marked with Note 1 are 25% aqueous solutions by weight. Ammonium chloride is 1.07, ammonium hydroxide is 0.91, and ammonium sulfate is 1.15. Additionally, aniline is 1.02. Argon has a molecular weight of 39.94, a boiling point of minus 302 degrees Fahrenheit, and a freezing point of minus 188 degrees Fahrenheit. Bromine has a molecular weight of 159.84 and a liquid-specific gravity of 2.93. And carbon tetrachloride has a molecular weight of 153.84 and a specific gravity of 1.59. Carbon dioxide is CO2, with a molecular weight of 44.01 and a boiling point of minus 109 degrees Fahrenheit. Carbon monoxide is CO, with a molecular weight of 28.01, a boiling point of minus 314 degrees Fahrenheit, and a freezing point of minus 220 degrees Fahrenheit. Chlorine is Cl2, with a molecular weight of 70.91 and a boiling point of minus 30 degrees Fahrenheit. The table continues at the end with chromic acid, citric acid, and copper sulfate aqueous solution at 1.17.
I would like to introduce the vapor pressure column header of the physical constants table. This column represents the vapor pressure, with a reference temperature of 70 degrees Fahrenheit. The pressure unit is sig based on gauge pressure. Being gauge-based means that atmospheric pressure is set as 0, and any pressure exceeding that is displayed. Since vapor pressure is the pressure at which a fluid tends to evaporate at a given temperature, it is used to evaluate the risk of flashing occurring downstream of a valve.
I will now introduce the headers for the specific gravity and critical temperature columns in the physical constants table. This section contains the headers for specific gravity and critical temperature. The unit for critical temperature is degrees Fahrenheit. The specific gravity column is further subdivided in the following chunk into liquid and gas bases, specifically based on 60 degrees Fahrenheit. Critical temperature refers to the limit temperature above which a gas cannot be liquefied regardless of how much the pressure is increased. These critical point properties serve as an important basis for judgment when selecting valves for supercritical fluids or high-pressure services.
I will introduce the critical pressure column, the specific gravity reference, and the continuation of the table. The unit for the critical pressure column is SIA, based on absolute pressure. Specific gravity is noted based on 60 degrees Fahrenheit for liquids and based on gas for gases. Critical pressure refers to the minimum pressure required to liquefy a gas at the critical temperature. At the end of this chunk, there is an indication that the physical constants table continues, showing that the table extends to the next page. For reference, writing liquid-specific gravity as 60 degrees Fahrenheit means the ratio of the fluid density to the density of water measured at the same 60 degrees Fahrenheit.
I would like to introduce the boiling point column of the fluid properties table. This column shows the boiling point of each fluid in degrees Fahrenheit, based on 14.696 IA, which is 1 atmosphere of standard atmospheric pressure. Since the boiling temperature changes if the pressure changes, even for the same substance, the table fixes the pressure reference at 14.696 IA so that all fluids can be compared under the same conditions. This boiling point value serves as the starting point for reading the subsequent fluid data table.
The boiling point column we saw previously continues with the same header in the next section because the table is long. The reference pressure remains 14.696 IA, and the values are in degrees Fahrenheit. Since the table is continuous across multiple rows and pages, confirming that this same boiling point reference applies to the subsequent fluid rows allows you to read the table without interruption.
This table summarizes the molecular weight, boiling point, and specific gravity of general non-hydrocarbon fluids. Each row is read in the order of fluid name, chemical formula, molecular weight, boiling point in degrees Fahrenheit at 14.696 IA, and then gas-specific gravity and liquid-specific gravity. Gas-specific gravity is a relative value with air set as 1, and liquid-specific gravity is based on 60 degrees Fahrenheit versus 60 degrees Fahrenheit. For example, ether has the chemical formula C2H520, a molecular weight of 74.1, a gas-specific gravity of 0.74, and a liquid-specific gravity of 2.55. Fluorine is F2, with a molecular weight of 38 and a boiling point of -305 degrees Fahrenheit. Helium is He, with a molecular weight of 4.003, a very low boiling point of -454 degrees Fahrenheit, and a light-specific gravity of 0.18. Hydrogen is H2, with a molecular weight of 2.016, a boiling point of -422 degrees Fahrenheit, and a specific gravity of 0.07. Hydrogen sulfide is H2S, with a molecular weight of 34.07 and a boiling point of -76 degrees Fahrenheit, and hydrogen chloride is HCl, with a molecular weight of 36.47 and a boiling point of -115 degrees Fahrenheit. Mercury is Hg, with a molecular weight of 200.61 and a very heavy liquid-specific gravity of 13.6. Glycerin is C3H803, with a molecular weight of 92.09 and a specific gravity of 1.26, and nitric acid is HNO3, with a molecular weight of 63.02 and a specific gravity of 1.5. In this way, non-hydrocarbon fluids such as acids, alcohols, halogens, and inert gases can be compared in a single table.
I would like to introduce the vapor pressure column of the fluid properties table. This value is the vapor pressure measured at 70 degrees Fahrenheit, and the unit is sig, which is gauge pressure. Vapor pressure indicates the tendency of a fluid to evaporate at that temperature. The larger the value, the more easily it vaporizes at the same temperature. Following the boiling point and specific gravity columns seen earlier, this vapor pressure column is organized as an additional property for the same fluid row.
As the table grows longer, the vapor pressure column continues with the same header in the next section. The measurement reference remains 70 degrees Fahrenheit, and the unit is sig. Since the table is continuous over several rows, the vapor pressure values for the subsequent fluids should all be read as gauge pressure at 70 degrees Fahrenheit.
I will introduce the specific gravity, critical pressure, and critical temperature columns that conclude the fluid properties table. The specific gravity column represents the relative density of the fluid, the critical pressure column shows the critical pressure in SIA, and the critical temperature column shows the critical temperature in degrees Fahrenheit. The critical point refers to the limit of temperature and pressure above which the distinction between liquid and gas disappears. By knowing both the critical pressure and critical temperature, one can determine the region where a fluid behaves as a supercritical fluid. With these three columns added to the boiling point and vapor pressure columns, you can check everything from the molecular weight to the critical properties of each fluid in one table.
I would like to introduce a continuation of the table summarizing the physical constants of various fluids. This segment corresponds to the header of the critical temperature column. The unit for critical temperature is expressed in degrees Fahrenheit. This table is structured to list values such as molecular formula, molecular weight, boiling point, specific gravity, and critical temperature and pressure horizontally for each fluid, and the part you are seeing now is the header fragment pointing to the critical temperature column. Please keep in mind that this must be combined with the preceding and following fragments to form a complete multi-column properties table.
This fragment is the header for the boiling point column of the fluid properties table. Here, the boiling point is defined as the value measured under standard atmospheric pressure conditions of 14.696 SIA. The unit is degrees Fahrenheit. It is important to remember that 14.696 SIA is based on absolute pressure. Because they were measured at the same pressure reference, the boiling points of the various fluids listed in the table can be compared directly.
This fragment is also a boiling point column header with a reference pressure of 14.696 SIA and units in degrees Fahrenheit. Since the properties table is divided into multiple pages and columns, the same header appears repeatedly. Repeating the same pressure reference for each column is to maintain consistency, so that the data can be interpreted using the same standard regardless of which part of the table is being read. You can find the actual boiling point values in the subsequent data body fragments.
This fragment contains the core data body of the various fluid properties table. The table includes the fluid name, molecular formula, molecular weight, boiling point, critical temperature, and the specific gravity of both gas and liquid. First, for nitrogen, the molecular formula is N2, molecular weight is 28.02, boiling point is -320 degrees Fahrenheit, critical temperature is -233 degrees Fahrenheit, and the specific gravity is 0.81 for gas and 0.97 for liquid. For oxygen, the molecular formula is O2, boiling point is -297 degrees Fahrenheit, critical temperature is -181 degrees Fahrenheit, gas-specific gravity is 1.14, and liquid-specific gravity is 1.105. Sulfur dioxide has the molecular formula SO2, molecular weight 64.6, boiling point 34.4 degrees Fahrenheit, gas-specific gravity 1.39, and liquid-specific gravity 2.21. Phosgene has the molecular formula COCl2, molecular weight 98.92, boiling point 10.7 degrees Fahrenheit, and specific gravity of 1.39 for gas and 3.7 for liquid. Looking at acids, sulfuric acid has the molecular formula H2SO4, molecular weight 98.08, and specific gravity 1.83. Phosphoric acid is H3PO4, molecular weight 98.00, and specific gravity 1.83. And water is H2O, molecular weight 18.016, and specific gravity 1.00. For the aqueous compounds at the bottom of the table, according to Note 1, the specific gravity of a 25% by weight aqueous solution is shown. Potassium chloride is 1.16, potassium hydroxide and potassium carbonate are 1.24, sodium chloride is 1.19, sodium hydroxide is 1.27, sodium sulfate and sodium thiosulfate are 1.24 and 1.23 respectively. Zinc chloride is 1.24, and zinc sulfate is 1.31. Additionally, vegetable oil is 0.91 to 0.94, turpentine is 0.87, starch is 1.50, and sucrose or sugar solution has a specific gravity of 1.10. Finally, Note 2 indicates the vapor pressure at 100 degrees Fahrenheit in SIA, and Note 3 indicates the vapor pressure in SIA.
This fragment is the header for the vapor pressure column of the fluid properties table. The measurement condition is 70 degrees Fahrenheit, and the unit is sig, which is gauge pressure. Unlike the SIA used for the boiling point, which was absolute pressure, you must distinguish that sig is relative pressure based on atmospheric pressure. The vapor pressure value at 70 degrees Fahrenheit is used to evaluate the volatility of the fluid and its tendency for flashing or cavitation inside the valve.
This fragment is also a vapor pressure column header with a measurement condition of 70 degrees Fahrenheit and units in sig. This is a part where the same header reappears as the properties table is divided into several columns. Since the standards of 70 degrees Fahrenheit and sig are maintained consistently throughout the table, you can read the vapor pressure under the same conditions regardless of which column you are viewing. Please refer to the data body rows for the actual vapor pressure values of each fluid.
I would like to introduce the header items used to determine the state of compounds in the hydrocarbon physical constants table. The specific gravity listed here refers to the liquid's specific gravity based on 60 degrees Fahrenheit versus 60 degrees Fahrenheit. Critical pressure is expressed in psi, and critical temperature is given in degrees Fahrenheit. These three values are key physical properties used as a basis to determine whether each compound is a gas or a liquid under given operating conditions and to perform conversion calculations necessary for valve sizing. In the body of the table, these items are provided as specific numerical values for each compound.
I would like to introduce the unit notation for the critical temperature column. The values in this column are given in degrees Fahrenheit. Critical temperature refers to the upper temperature limit above which a compound can no longer be liquefied, no matter how much the pressure is increased. In other words, in the region above this temperature, liquefaction does not occur through pressure alone. This header pairs with the critical temperature values filled for each compound in the physical constants table, serving as the reference temperature for evaluating the state of each hydrocarbon.
I would like to introduce the volume column, which represents specific volume. The unit for this column is cubic feet per pound. That is, it is the specific volume, meaning the volume occupied by a unit mass of 1 pound. Specific volume is the reciprocal of density, which is pounds per cubic foot, appearing later. This value is provided as a state property for each temperature in the saturated vapor and saturated liquid state tables, and it is a reference item when converting flow rates to a volumetric basis or calculating volume.
I would like to introduce the density column. The unit for this column is pounds per cubic foot. Density refers to the mass contained in a unit volume and is the reciprocal of the specific volume or cubic feet per pound, explained previously. This value is included as a state property in the saturated liquid and saturated vapor state tables and is used when converting between mass-based flow rates and volume-based flow rates.